Hello everyone, this is Sunil, and in this video we are going to discuss some on electronic materials and devices. We'll take some questions on crystal structure, that means some related to defects in the solids, and let's say some vacancies are created, uh, and how we can calculate the fractional concentration. Second question, we'll discuss about how we can calculate the intrinsic concentration in a silicon and intrinsic resistivity in silicon. Then we'll discuss about the concept of Fermi energy and calculation of work function in the doped silicon in a p-type or n-type. And then we'll discuss about some questions on semiconductor related to transport behavior, that where the current densities, diffusion current density, drift current density will take into part. And then finally, we'll discuss some questions on semiconductor, that where that particular case study, when we take into consideration of different donor atoms, isotope atoms, and how can we calculate the other resistivity of that particular semiconductor. Okay, so fine. So let's start with the questions here. So first question is here, the energy formation of a vacancy in the copper crystal is 1 electron volt. Calculate the fractional concentration of vacancy in the copper at room temperature. It is clearly mentioned at room temperature you have to find out your fractional concentration. And another, you have to find out fractional concentration just below its melting temperature, that is at 1084 degrees centigrade. Neglect the change in the density, which is very small. So how can we proceed with this thing? Uh, let's say if n is the number of atoms per unit volume in the crystal, and the vacancy concentration is Nv. V is nothing but vacancy, N is the concentration. The vacancy concentration is Nv. Then Nv is equal to N into e to the power minus Ev by kT. What is Eb? E the energy formation of for vacancy to create. Okay. K is the Boltzmann constant and T. Now as per the questions, the energy formation for vacancy in the copper crystal is 1 eV. So this eV is nothing but 1 electron volt. So first you have to find out what is my fractional concentration, that is your Nb divided by N at 300 Kelvin, that is a room temperature. So if you can put all this value here and put the Boltzmann constant and temperature value, then it is the fractional concentration will come 1.3 into 10 to the power minus 17. Okay. Remember, this is a fractional concentration. That means you have to take the fraction. So that means there is no unit of it. Okay. So it is just a numerical value. So what is the thing? So here 1.3 into 10 to the minus 17. Okay. Now at temperature 1084 degrees centigrade, how it will the fractional concentration? First, you have to convert 1084 degrees centigrade to into equivalent Kelvin. Okay, so 1084 into 273 will be 1357 Kelvin. Then what will be my fractional concentration? Put all this value here. So finally, we'll get this fractional concentration is numerically equal to 1.9 in 10 to the minus 4. So at room temperature 300 Kelvin, it is 1.3 into 10 to the minus 17, and at temperature 1084 degrees centigrade, it is 1.9 into 10 to the minus 4. Second question. Given that the density of states related to the effective mass of electrons and holes in silicons are approximately 1.08 MeV and 0.60 MeV. MeV is nothing but your mass of electron, and electron and hole drift mobility at room temperature are 1400 centimeters per volt second and 450 centimeters per volt second. Then calculate the intrinsic concentration of silicon and then calculate the intrinsic resistivity of silicon. Now, this is a very important question, as uh, to find out the intrinsic resistivity of silicon, you have to calculate the intrinsic concentration first. Then we can calculate the intrinsic resistivity. So how can we proceed? In this case, first you have to calculate the effective density of state at conduction band and valency band edge. And this is nothing but as per the relation If Nc is the effective density of state at conduction band edge, so it is 2 into 2 pi m star kt by h square to the power 3 by 2. M star is nothing but your effective mass of electron, h is Planck's constant, k is your Boltzmann constant, T is your temperature. Similarly, the effective density of states at valency band edge is 2 into 2 pi into mh star kt by h square to the power 3 by 2. Mh star is nothing but effective mass of hole. Okay. So all these values are given, so you can find out Nc and Nb, and after finding out, then we have to find out the intrinsic concentration. That is nothing but Ni is equal to square root of Nc into e to the power minus Eg by 2 kt. What is Eg? Eg is nothing but your band gap. As you know, for semiconductor silicon, it is 1.1 electron volt, right? So if we can put all this value, then we can find out intrinsic concentration as 1 into 10 to the power 10 per centimeter cube. Then how can we find out resistivity? Resistivity we can find out if we can find out conductivity first. Then reciprocal of your conductivity will give resistivity value. The conductivity is as per the relation, it is E n mu E plus E p mu H. What is E? E is the electronic charge, N is the electron concentration, mu is the mobility of electron, mu H is the mobility of hole. This is hole concentration. Okay, but your your whole concentration is equal to electron concentration is equal to your intrinsic carrier concentration. So it will be ENI mu n plus mu h. So conductivity we can find out as 3 into 10 to the minus 6 ohm inverse centimeter inverse. So what will be my resistivity? Is nothing but reciprocal of conductivity. So it will give your resistivity is equal to 3.3 into 10 to the power minus 5 ohm centimeter. Now next question. Consider a doped silicon substrate at room temperature where the Fermi potential is 0.2 eV. If the electron affinity of silicon is 4.15 eV, then calculate the work function of the doped silicon p type and n type and compare. Explain with Venn diagram. So in this case, we have to find out what is my work function of the p type and n type semiconductor, and we have to compare that how this work function will affect the overall silicon substrate, and we have to take a comparison of the work function of these two p type and n type. Everything we have to explain it in with the help of Venn diagram. So let's see now the energy band diagram of p type silicon. Let's say if we take into consideration, so this is my free space, that is denoted as E naught, and this is conduction band edge, that is denoted as EC. Now intrinsic Fermi level is denoted as EI. EFP is the Fermi level for p-type semiconductor. E for Fermi level, P is for p-type silicon, and EV is the valency band. Now, at is a p-type silicon substrate, there is extra energy level is created because of acceptor atoms. So that is this acceptor is level is created just above your valency band, and that is nothing but your Fermi level. So we have to remember that this Fermi level is always created above the valency band for a p-type silicon substrate. Now this intrinsic Fermi level is always in between your Anderson and valency band. So it is irrespective of which type of semiconductor. Uh, so irrespective of any kind of semiconductor, whether it is intrinsic or extrinsic, this intrinsic Fermi level is always lies between your conduction band and valency band. And this band gap is nothing but between your conduction band and valency band is 1.1 eV. So this electron affinity value is given already 4.15 eV. So this is your band gap between EC and EB. So this one we can divide, because as I said, your intrinsic Fermi level is in between your conduction and valency band. So from EC to EI, so it will be 0.55 eV, and from EI to EB, EB also 0.55 eV, because 1.1 divided by 2 is equal to 0.55 eV. Now this Fermi potential is already given 0.2 eV as per the question. Fermi potential is 0.2 eV. Now what is my work function? Work function is the amount of energy required to move the electron from the Fermi level to the free space. Right. So what is my then total work function will be 4.15 eB, then plus 0.55 eB plus 0.2 eB. So total will be 4.9 eB. So work function for the p-type silicon substrate is 4.9 eB. Now let's go to the n-type silicon substrate. Uh, how the work function is. Now in this case, this Fermi level is situated just below your conduction band. Okay. Now that is the extra energy level is created by the donor atoms. So if you can see here, this AFN, that is nothing but Fermi energy level of n-type silicon, is created just below your conduction band. Now from conduction band to the free space, it is 4.15 eB, and if it is 0.55 eB, because intrinsic Fermi level is placed just between your conduction and valency band, so it is 0.55 eB. So if it is 0.55 eB, then the between your Fermi level of n type and conduction band, it is 0.35 eB. So because 0.55 minus 0.2 will be 0.35 eB. So what will be work function? As I said, work function is the amount of energy required to move the electron from the Fermi energy level to the free space. So, so this is my work function. So 4.15 pb plus 0.35 pb. So this is my total work function. So when it comes to be 4.5 pb. So we see that the work function of a n-type silicon substrate is less than the work function of the p-type silicon substrate. Okay. Now let's go to the next question. The electron concentration in a sample of non-uniformly doped n-type silicon is at 300 Kelvin, that is room temperature, varies linearly from 10 to the power 17 per centimeter cube at x is equal to 0 to 6 into 10 to the 16 centimeter cube at x is equal to 2 micrometer. Okay. So assume a situation that electrons are supplied to keep this concentration gradient constant with time. If the electron charge is given 1.6 into 10 to the minus 19 coulomb and diffusion constant is given Dn is equal to 35 centimeters square per second, then find the current density in the silicon if no electric field is present. To find out what is my current density. Now, as you know, the current density, when you take into consideration, we have to take the diffusion current density and drift current density. But drift current density is dependent on the electric field. But is there any electric field is here? No, because it is mentioned that this electric field is constant. Okay, because it mentioned here that no electric field is present. So that means electric field is zero here. So electric field is, there is no electric field. So E is equal to 0. So what will be my current density? The current density will be only due to the diffusion current density. Now for that we have to find out first concentration gradient. So this concentration gradient we can find out from the given data, because it is varies from 10 to the power 17 per centimeter cube x is equal to 0 to 6 into 10 to the 16 per centimeter cube x is equal to 2 micrometer. So if we can calculate the concentration gradient, so it is minus 2 into 10 to the 20. So what is my current density? So it will be 35, because diffusion constant is already given 35 centimeters square per second. So charge of electron into concentration gradient. So it is somewhere coming to be minus 1120 ampere per centimeter square. Now, next question. A sample of germanium is doped to the extent of 10 to the 14 per centimeter cube donor atoms and 7 into 10 to 30 centimeter cube acetons. At room temperature, the resistivity of pure germanium sample is 60 ohm centimeter. If the applied electric field is 2 volt per centimeter, then find the total current density. How can we solve this question? Now, for that, as you know, pure germanium, your intrinsic carrier concentration is equal to your electron concentration and hole concentration. Okay. So, your intrinsic carrier concentration is equal to electron concentration equal to hole concentration. So, what is my intrinsic carrier concentration here? Conductivity divided by mu1 plus mu2 into charge. What is mu1? Charge of electron, mobility of electron. Mu2 is the mobility of hole for this germanium. Mobility of electron is for electron. is 3800 centimeters square per second, and mobility of hole for German is 1800 centimeters per second. If we can put this value here, then we can get the intrinsic concentration is 1.86 into 10 to the 13 electron per centimeter. Now, for intrinsic silicon, if you take into consideration, as you know from mass action law, your product of electron concentration and hole concentration is equal to your intrinsic carrier concentration square. That is P into N is equal to Ni square. Also, we know charge neutrality equation that if P the hole concentration, N is the donor concentration, Na is the acceptor concentration, and N is the electron concentration, then P plus Nd is equal to Na plus N. Then what is my P minus N? Na minus Nd. Okay. So we have now two equations. One is P into N is equal to Ni square. Ni just now we find out here. And P minus N is equal to Na minus Nd. So that is minus 3 into 10 to the 13. So we have two equations here. This one and this one. P into N is equal to Ni square and P minus N is equal to minus 3 into 10 to the 13. Now, if you can solve these two equations, then we will get electron concentration as 3.88 into 10 to the 13 per centimeter cube, and hole concentration is 0.88 into 10 to the 13 per centimeter cube. So, what is my current density here? N plus into mu n plus P into mu p is your charge into electric field. Okay. So, if we can put this value here, then finally we will get 52.2 per milliampere per centimeter. So this is the current density. This is the question. Find the total current density. So the total current density is 52.2 per milliampere per centimeter. So I hope this problems with solution has given many important details about different questions on electronic materials and devices. And I hope this video uh, is informative. If you have any queries or any doubts, feel free to address those comments in the chat box, and also in the in this if you have any problems and then any solution, any queries, you can put in the chat box also, and you can ask any queries. If you have any doubts, also that also you can ask. So I hope this video finds informative, and hope this will help you in preparation for any questions on electron metals and devices. Thank you, everyone.